Finally, our last speaker, Felix Biessmann, next to me. Everybody knows Amazon. Who has heard of the Einstein Center? Who knows my famous university, Beuth Hochschule? Very good. And I'm actually super proud to have one of the professors. When I went there 20 years ago, we didn't have that good professors, so apparently now they actually have. So thanks for coming, Felix. Really excited to have you here. Also, Amazon is very known for ML, and so this is one of the guys actually helped them build it. So really excited to have you here. Thanks for coming, and I put you on.
I think I'm good. Yeah. Am I? Can you hear me okay? Thanks. Hi. So thanks a lot for the kind introduction. And also, thanks a lot for the invite. Thanks a lot for the audience. Thanks for staying until the last talk, and thanks for the previous speakers for their some really inspiring talks, especially Calvin's. That was really, yeah. I liked the previous talks because I couldn't have come up with a better, list of talks to set the stage for what I'll be talking about on a more general level. So this is mostly work done at Amazon Research. By a great team of other scientists, including Sebastian Schelter, Dustin Lange, and many others. And I've been with Amazon Research for more than 5 years, and we build infrastructure and products with AI, machine learning. And we learned many things the hard way. And because we want everybody to profit from those experiences, I'll talk about some of the stuff that we built. We actually formed a team that is dedicated for using machine learning to improve data quality for machine learning or other purposes. And so everything that we do is published and open sourced. So feel free to just look it up on GitHub or use it. We're really happy for feedback or pull requests. Right. So there are two kinds of people. Some have to care about data quality, like Dilbert, and some don't want to get bothered with it. And at the end of this talk, I hope that I could convince everybody that it's really important to think about data quality. And we had many examples in the previous talks that alluded to this point. Why is it important to talk about data quality when you're doing machine learning for production systems? From a manager's perspective, it's really important because there are legal requirements. If you put something in production that uses machine learning, you have to be certain that what you're predicting is not biased, for gender or ethnicity. If you think about all the major, all these epic fails that made it through the media to the media, racial biases and so forth, all these things. I mean, in all those cases, the algorithms didn't do anything wrong. The algorithms were fine. It was the data that was wrong. If you have a racist, group of police officers that produces the data that you use to train your model, of course your machine learning model will be, racist. And all of these things, you have to. For us, that falls under data quality. The algorithms, there was nothing wrong with them. Another example is if you think of. I just recently talked to somebody from a startup who they build autopilots for air transport systems. And in those, in some applications, you really have to be sure that you know what your system will do. And if there's a convolutional neural network in there, then, as we've seen in the previous cases, it's not that easy. You can, fool these networks pretty easily, and you have to. When you put these things into production, so far there are no autopilots that use that stuff. And I know from this guy that they're having a really hard time to convince the institutions that take care of these things to put that stuff in production. So that was from a manager's perspective. From a scientist's perspective, everybody knows, everybody who works with actual data and machine learning systems knows that data quality is your most important hyperparameter. There are so many examples when you think about, you can use Bayesian global optimization or grid search, random search, and do everything you want. If you don't have good quality data, your system will not perform well. And in the previous talk, there were many examples in that direction. So as a scientist, you should care about that. And as an engineer, and this is So a special thanks to Kamal from Kareem. I really liked that paper that you showed, that figure from the Scully paper. We'll see that again in a bit. So data quality, for an engineer, data quality is really important because most of the worst hidden technical debt in AI systems comes from that. And so why is that? So this is how the world looks like if you come from a university. If you have a PhD or a master's in machine learning, you think, oh yeah, I'll get my data from somebody, I'll just do my model, and then I'll serve some predictions, and I'll be rich. And unfortunately, like most of the researchers I've been working with, they learned it's not like that, and they learned it the hard way. What I mean by that is pretty much the figure that, that Kamal showed, which is from the Scully paper. It's one of the, I think, most underestimated papers out there because when you put machine learning in production, you will feel a lot of pain because of stuff that's not related to machine learning. And all of that pain is subsumed in that paper, essentially. So actually, machine learning is really just less than 10%, I would say, of your work. And all the other stuff is data collection, feature extraction, data verification, configurations, analysis tools, all that stuff that you don't want to care about if you want to do science. Or this is from the Scully paper, and there were follow-up papers, and this is now there are conferences for that stuff for machine learning systems. Back then, people didn't really care too much about it. Now, the important point is that all of these orange boxes are related to data quality. And you should be worried about that, because the size of these boxes is proportional to the time people need to fix these problems. And time is proportional to the money, so it's a huge cost factor. What I'll be talking about, just 3 quick examples of what we've been doing in our team at Amazon Research. And it's, again, open sourced and published, so feel free to look that up if you're interested in the details. So first, I'll be talking about measuring data quality. And we thought we should put forward something like unit tests for data. Everybody knows unit tests for software systems. For machine learning systems, you need to be sure that your data is OK. If you have found some data quality issues, then you might want to fix them. And we build tools, machine learning tools, to do that for you automatically. And then another problem is when you put stuff in production, many of these problems came up earlier in the previous talks, but you also want to be able to predict how bad your model will perform on tomorrow's data, for which you don't know the labels. So measuring data quality. So maybe some of you can relate to that. And it's funny because it's true. Many people don't write enough tests for their software, but it's actually their fault when stuff goes wrong, because there are so many tools for unit testing your data, for doing integration tests. Just use them, and you will have a lot less problems. Now, what we wanted to suggest is to actually unit test your data, and it's very simple. So we built something that is it has a super simple API. People use it, so we have, internally we use it in at Amazon's data warehouse, and we found that many people, at first I thought, wow, this is too easy. We don't need to build that. Everybody can do this by themselves, but it's actually, not easy to build these things in a robust, scalable manner. So this stuff is built on top of Spark. It was published last year at VLDB, and it's called DQ, the library on GitHub. And this is an example of a suite of unit tests for data. So you can, really simple things like if you want to, So you can, for instance, just check whether the data has enough columns, whether the columns are complete, whether the distributions of the data are like what you want them to be. And this works on partition data, so it's incremental. You don't, if you have a terabyte of data analyzed and another 100 gigs come in, then you don't need to run it on the entire batch. So that's unit tests for data. The next thing, once you have identified data quality issues, then you might want to fix them. And the most important data quality issue is missing data. When you think about so here's an example from Amazon. Amazon's use case on a retail page, you might have this is maybe some data that you're interested in. It's a product catalog. You have product types, categorical values, maybe some free-form text and some other categorical values, and then there is some stuff missing. But every human that looks at this would probably know that, okay, yeah, this color should be yellow because it says so in the text. So some of these cases are really simple, some are more, difficult, and you might say, well, there's a lot of work on imputation, let's use that. And that's what I thought. So when we started this 3 years ago, I looked up in the literature, what can we use for that? And it turns out that pretty much all the work on imputation is for matrices, not for tables. And by that, I mean for tables with numeric values only. And maybe categorical values, which you can easily transform into numerical values. And all of that stuff was built for super tiny data sets. So yeah, we just built something that is a little bit more scalable, more robust. It's also working better than anything that we tested it against, which is a lot. It also works for missing completely at random, missing at random, and missing not at random. Like in the last two were pretty hard conditions, actually. It's also published last year at SICM, and we released an open source package. It's called DataWig, like a wig. I mean, the data won't look great after it, but it will be covered somehow. And of course, there's a lot of machinery in that package to make sure that the models are well calibrated, and for hyperparameter optimization and all that stuff. And for explaining the model's predictions, for instance. So that was that. Now, when you put a model in production, and we've heard a couple examples of that today, we were in this situation often that we had some customers and that they wanted to impute some missing values, and actually, so some of these people who used our software, of the internal Amazon customers, they didn't know how to code before. They were product people. We built the API to be so simple that actually those people also could use it. But when they gave us the training data, or when they looked up the training data to train the model with, we often had pretty difficult cases of dataset shift between the training data and the data that they used to, that they applied the model to. Now, and this is one of the most important problems if you put machine learning models in production. So you first train a model, then you validate it. That's all offline, and then your model goes live. And then there are these challenges associated to, for instance, adversarial attacks or other data shifts that might predict your predictive performance. And then also there is the question, when should you retrain your model? And so this is pretty recent work. There's just a short paper that will be presented in Amsterdam at SIGMOD in a couple of weeks. What you see here is, it's a very, very simple approach. We just train a meta model on some perturbed versions of the original training data, and then we test how well that could work when you want to, how well that predicts the actual performance of your model when it goes live under shifts of the data that you don't know. On the x-axis, you see the true performance of the model. And on the y-axis, you see the predicted performance. And in many of these cases, it actually works okay-ish. And we're now looking into more, even worse shifts or perturbations of the data. And so to summarize, data quality is really essential for managers because it's a legal issue as well. For scientists, because you want to have accurate predictions, and it's important for engineers because it's a huge cost factor if you don't, have your data in shape before you use it for training or predicting. And we, propose some machine learning methods for automating these testing cases, so unit tests for data, for imputing missing values or correcting wrong values. And we also are looking into predicting machine learning pipeline performance on the dataset shift. Thanks.
Thanks so much, Felix. Questions? Oh, in the back.
Thanks. I like your library so much I use it. We're actually using it already. It's really great. I guess the competition is TFX, data validation, and the fact you're Scala only. right now, and a lot of people want to write end-to-end pipelines in Python.
Yeah.
What's the roadmap there?
Yeah, I'm not sure whether I should be talking about that, but so actually we had so my manager he graduated from the University of Potsdam, and he just got a whole batch of students from that professor Felix. He's a seasoned scientist in this field, and so the plan is to roll out something that works for any database essentially. But it's so we have. I mean, I've seen prototypes that work, and so it should be doable to.
Sorry, database.
Sorry.
No, I meant programming like Python support, and then.
I thought you were worried about the Spark Scala constraint. No.
No. Well, yeah. I mean, you'd like to have PySpark, I guess.
Oh, PySpark. Yeah.
Yeah.
So yeah, I actually personally, I mean, everything I'm doing is in Python, but
Yeah.
PySpark, with this, many layers of stack traces, I'm not really a huge fan. But I mean, PySpark, of course, supports. So I think you should be able to use it, but we don't support PySpark explicitly. But we are working on something that works for standard SQL databases.
That's just TFX. Like, how do you compare? Because TFX.
With TFX, yeah. So actually, so the Google team is actually one of the only teams that So they do something very similar, and we also cite our papers, and they have. So what I know from the TFX work is that it's very limited in terms of how. So we would compare it to the last work here, this pipeline performance prediction. And their stuff, they only compare univariate shifts of single features, essentially, when it comes to validating the data. So that we do a little bit more than that. But it's great work. I'm a huge fan of that. Yeah.
Okay. I think then this concludes the evening. Thanks so much. Big applause to Felix.